All right, so some of us were working on the discrete random variable with a binomial distribution, and we were having a hard time thinking just about what the word mode means. So I'm looking here at problem 7, and not rather than just giving the answer, I want to try to make sure we understand what it means to have a mode even with a binomial distribution. And so, for example, I'm not going to do the 2n as my first example. I'm going to do a binomial distribution. Let's just say that there are, um, let's do something simple, 4 trials, each with a probability of 1/2. So then what we can do is start calculating all of the different possible outcomes here. So let's say the probability that x equals 0. So the probability that x equals 0 means you had zero successes. So the way to do that is 4 choose 0, 1/2 to the 0, because we're saying there's 0 successes, and 1/2 to the 4th. That's 1/2 to the 4th. So at the end of the day, 4 choose 0 is 1, 1/2 to the 0 is 1. So this is just 1 over 2 to the 4th. So I guess that's 1 over 16. We can keep going and get p of x is equal to 1. P of x equals 1 is going to be 4 choose 1. So now we have 1 success, so 1/2 to the first power, 1/2 to the third power, and that's going to be 4 times, we still have 1/2 to the fourth power, so 4 times 1/16, and so that's just going to be 1/4. So a lot more common than x equals 0. Then if we look at b of x equals 2, very similar. 4 choose 2, 1/2 to the second power, 1/2 to the second power. The only thing that's really different here is 4 choose 2 is a little bit bigger. 4 choose 2, off the top of my head, I guess I'll just work it out. 4 factorial over 2 factorial, 2 factorial times 1/16. So let's see, 2 times 2 on the bottom makes 4, so we have 3. Does that come out to be 6 over 16? That should work. And then here's the nice thing about the binomial distribution. When you have a probability of 1/2, the next 2 values of p of x equals 3 is going to equal p of x equals 1, because 4 choose 3 is equal to 4 choose 1, and all that happens is I would interchange the 1 and the 3 right here. Same idea if I do p of x equals 4. And this assumption is only valid because I have x is equal to 1/2. We have the equal probability of a success or a failure. So if you look at the 5 total possibilities here, you can see that the one that is the most common is x equals 2. And the one, x equals 1 and x equals 3 are the next most common, and then x equals 0 and x equals 4 are the least common. And that kind of makes sense with what you would expect. If you think of this as flipping a coin 4 times, you would expect there to be 2 heads and 2 tails. That would be the most common outcome. It'd be less common to get 1 and 3 of either type, and then it'd be the least common to get all of one type and none of the other. This same logic then extends out to deal with problem 7, because we have an even number of trials and an equal success of probabilities and failures. And so I know basically, instead of writing p of 4 is equal to p of 0, I'm just going to change, and I know that the probability that x is equal to 2n has to be equal to the probability that x is equal to 0, the probability that x equals 2n minus 1 has to be equal to the probability that x equals 1, etc., etc. And then in the middle, I just get the probability that x equals n. And then this is going in increasing order of probability. As you go down the list, the outcomes get more and more likely. And so the most common outcome, the mode, would be n. And then just like the mode on my simple example in red was 2. So then to answer the second part here, the probability that x equals n, what we can do, let me clear my screen, probability that x is equal to n is going to be 2n choose n times 1/2 to the n times 1/2 to the n. And initially, when I was doing this, I thought I'd be able to solve that analytically. And here's how far I got. 2n factorial over 2n minus n factorial, and then we can have 1 over 4 to the n. And this doesn't really cancel out very nicely at all, because the 2n factorial, it's not like you can cancel that with an n factorial, because it counts down from 2n down to n, and we need to make this equal to 35 over 128. So if you were to do this by hand, I guess the next thing you would do is just start plugging in n equals 1, n equals 2, and going from there. But luckily, this is the calculator portion of things. So you can actually type that thing exactly into the calculator. You can even use this version of it right here and type it in with the combination coefficient, the combination NCR idea. So 2x choose x, and then 1/2 to the x, and another 1/2 to the x, or you can simplify that if you prefer. And then if you just look at your table, let's see, can we see that? There you go. You can see it's errors for negatives. So you can't have a negative number of trials. If you have 0 trials, you'll just get 1, and you're just working down until you get 35 out of 128, and so that's close to a quarter. So either n equals 4 or n equals 5. So I'm just going to go and do 35 over 128. It tells me I'm looking for 0.273. Go back and look at my table. Looks like that's n is equal to 4. And just to be overly checking my answer, I'm going to try 8 factorial over 4 factorial times 4 to the 4th, and see if we can get this to cancel out. So I can write that as 8 times 7 times 6 times 5 over 4 times 3 times 2 times 4 to the 4th. We can knock down a 4 and a 2 and an 8. We can knock down a 3 and a 6 and make that into a 2. And so what we can see here is we have 35 times 2 over 4 raised to the 4th. And like I can see the 35 is matching up already. And if you think about 4 to the 4th, let's see, 4 to the 4th, we go 4, 16, 64, 256. And that's how we cancel it down to be the requested probability right there. So there you go. Please comment or ask for questions if there's anything I can do to help.